Welcome you all for this video lecture on code generation for code optimization. So which is the final phase of the compiler. So in this particular playlist, we are going to cover a topic of issues in code generation, runtime storage management, basic blocks, tag representation, heap call optimization, principal source of optimization and optimizations of basic blocks. To start with, in this particular video, we will be covering about the issues in design of code generation and runtime storage management. So before getting into the next issues, so we should be knowing that what is code generation. So this is the final phase of the compiler model. So which will be taking the input from the intermediate representation of the source program, and it will be producing the target program. So then the target program can be an assembly code or a bytecode. That depends on the platform. So the code generation techniques presented below can be used whether or not an optimizing phase occurs before code generation. So a code generator converts the intermediate representation of source code into a form that can be readily executable by a particular machine. So design of the code generator should be done in such a way that so that it can be easily implemented, tested and maintained. So now we will see about what are the issues that we have in this particular code generator. First issue will be the input of the code generator. Next one, target program, memory management, instruction selection, register allocation and evaluation order. To start with, first issue is the input to the code generator. As we know that the input to the code generator contains an intermediate representation of the source program, and we will also add the information from the source table. So intermediate representation may have several choices like postfix notation, syntax tree and three address code. So we were well known about this syntax tree and three address code, and in the three address code we have different representations or notations of three address code, that what we call it as the quadruple, triples and indirect triples. So here we assume that the front end produces low-level intermediate representation, that is, values of the names in it can be directly manipulated by the machine instruction. So the code generation phase needs complete error-free intermediate code as an input requires. So whatever the input that we give for the code generator, it should be error-free. First issue. Next one is the target program. So the target program is the output of the code generator. So the output can be assembly language. Okay. So it will be like a subprograms which will be having some set of instructions. And then next one is the relocatable machine language. So which is nothing but it makes the process of code generation which is very easier when it comes for the relocatable machine code. Similar to it, the third output can be an absolute machine language. So it can be placed in a fixed location in a memory and can be executed. Whereas if we take a relocatable machine code, we can even take a bytecode as an example, that is Java bytecode as an example. So here we will be compiling the program, and the entire source code will be converted to a bytecode, and that particular bytecode is a machine independent one. So which means I can able to run it on any kind of platforms, right? So that, and similar to it, if you take a Java program, we have we can write the programs in different types of classes or subroutines or procedures, and all those procedures can be compiled and kept in different locations of a memory. And in your language processing system, we have a one part called loader and linker. So what this linker will do is that it will link all the programs, subprograms together, right? So that what we call it as a relocatable machine language. So it will, that linker will link all the programs and it will be ready for the execution. So in this, the target machine. So here, this is a very most important thing. The first one, what we are saying is the assembly level language. So whenever we choose an instructions while writing an assembly level language, we need to we need to follow some features, or we need to address, or we need to look into some features. So here, the input code generation requires a thorough understanding of the target machine architecture and its instruction sets what we have to write. So consider the hypothetical machine with the following features. The instructions are byte addressable. So we know that few instructions are word addressable and byte addressable will be there. Think of that the instructions are byte addressable where a word is 4 bytes. We know one word is 4 bytes. So All these things will be having a general purpose registers like R0, R1 up to Rn-1. We have certain set of registers will be there. So here we will be writing the instructions. So instructions are nothing but instructions are two addresses. One of the form, that is the operator will be there. What is the operation that we need to do? Then source comma destination. Where here the OP stands for the opcode, right? So here is an example. Move is one instruction, that is an opcode that we call. It will be moving the content of source to destination. Then add is nothing but it add the content of source to destination, and the result will be stored in the destination. Whereas similar to it, the subtract will also find the difference between the source and destination values, right? Why here we are going to talk about this is that whenever we write an instruction set, we need to consider the cost of it, right? So here is an example for that. This is we have already, if you have gone through the computer architecture, we would have already studied about the different modes of instructions that is there, right? So here this is an absolute mode which is a form M, and here which just means it will be concentrating on the memory, right? So this is an absolute addressing and it involves one memory unit and incurs an additional cost of 1. So here this cost is nothing but how many words that we need for an instruction to be executed. That is what we call it as a cost. So if we see some example, then this will be clear. Then registrar, which will be involving the register for this, and the registrar doesn't involve any additional cost for it. And then the indexing, like for example, if we are using something called as an arrays and all, we will be going with the indexing mode. So this is the form which we will be having. Here the constant plus the contents of the register we will be taking. So here the added cost will be 1. So index addressing, where the register holds the address to operate upon and it's offset by the value C. Oh, that is the index value, we call it as an offset here. Next one, indirect register. Okay, so here the star of this is how we will be representing the indirect register. So content of R. So the content of the register are looked upon to find the address of location of to operator. See, it is very simple that this register will be holding the address of some other register or some other memory location. Right. Next one, indirect index. So this is index and this is indirect index. Similar to it, this is the combination of index and indirect register. So which will be having the added cost of 1. Last one will be the literal, which is nothing but a simple constants will be there, and the additional cost will be the added cost will be 1. So how we are supposed to select an instruction? For example, if any code is being given for you, so how we should write an assembly code, and to write that assembly code, how we should choose the instruction set. So after understanding all these types of addressing mode, the choice of instruction depends on the cost effectiveness of the instruction, right? So here the cost of the instruction is defined as 1 will be the standard thing, that is for the opcode, 1 plus cost of source mode. So as we know that the instruction is of two address, one is op, source and destination. So here 1 plus the source, what is the cost of the source, and the cost of the destination. This is how we will be calculating the cost of the given instruction. Here is an example for this. So here move of R0, R1. So here it stores the content of R1, R0 into R1. So the cost will be 1. Okay. So here the register involves 0 cost, and the cost of the cost for the particular move will be 1. And similar to that, here MOV, that is the op, will take 1 cost. The cost of it will be 1, and register will not take any cost. So this is what we have discussed in the previous thing. Register, we will not have any cost over it. And here memory will take a cost of 1. So the total cost of this particular instruction will be 2. Okay. Similar to it also, we have moved for this one, and then so here for this one we will be having 1, and for this memory we will be having another 1 plus 1. So the total cost will be 2 here. And for this one we will be having cost 1, and here we have something called as the indexed mode. Okay, indexed mode. So for this also it will cost 1. So 4 of R0 cost 1. That 4 is a constant of the, and then R0 is the register, and then again the memory will cost 1, and other than that the move instruction will also cost 1. So the total cost of this particular instruction will be 3. Right, similar to it, yeah, this is for 1 and this is the it is the combination of the previous one, that is what we call this as an indirect and the indirect indexed. Okay, so here also for this one it will be cost 1, for star 4 of or not cost is 1, for memory cost is 1. So 1 plus 1 plus 1, the total cost is 3. Okay, and here for this it will be storing 1 to the register. So hash 1 cost is 1, and for the move cost is 2. So the total cost will be 1 plus 1, it will be 2. And similar to it, this for add the cost is 1, for this one cost is 1, for this indirect indexing cost is 1. So the total cost of this particular instruction will be 3. So this is what is the simple the most widely used instructions that we will be using for a simple operation. Here I have given one example here. If I take this particular expression a equal to a plus 1, so I will be writing the instruction set here. So this is one type of instructions I can use for performing this operation, that is the assembly level language. So first I'll be moving the value of a to register. Then what I'll do is that I'll add 1 to the register, and then again I'll move the register value back to a. That is a equal to a plus 1. If I see to this particular instruction cost will be 2, and this particular instruction cost will also be 2. Here also it will be 2. So 2 plus 2, the total cost will be 6. Okay, and the same for this a equal to a plus 1, I can write this particular instruction also, that is add of hash 1 comma a. Instead of moving the a value to register, perform addition, and then moving back the value from register to the variable a, what I'll do is that add hash comma a. So if you take this, for this add 1 cost is 1, for this hash 1 the cost is 1, for this add the cost is 1. So the total cost of this entire instruction itself will be 3. Okay, and then next one, instead of doing that also, I can even directly go with one instruction called INC. This is just, it will increment the value which is present inside E. So the total cost will be, for this INC the cost is 1, for this A the cost is 1. So 1 plus 1, it will be the total cost of this particular instruction will be 2. So when I compare for this particular a equal to a plus 1, I have written 3 different types of instruction set. So which will be cost effective? This one. So this is how we will be choosing the target program or the target language. So based on the, how the instruction cost are, based on the instruction cost, we should efficiently choose the instructions in converting your intermediate representation to an assembly code. This is also another example that I have given you, so you can have a glance over that, right? Next issue that need to be addressed is the memory management. So mapping the names in the source program to the address of data object is done in the front end and the code generator. The name is the 3 address statement, refers to the symbol table entry for the name. Then from the symbol table entry, a relative address can be determined for the same name. Okay. The next one, local variables or stack allocation in the activation record, while the global variables are in the static area. So in a memory, we will be having something called as a cache will be there, then static memory location will be there. Similar to it, we will be having the heap and the stack also, right? So all your local variables will be present in the stack location, that we call it as an activation record, whereas our global variables will be in the part of the static area. So here next issue that need to be, so where we will be placing all the things. For example, if function call is being done, we'll be placing all the variables inside the stack, and once the function call or execution is over, all those things will be removed. For example, if we are having any static variables or the global variables, all those things will be placed in the static area of the memory. Right? So for this we will be discussing. Next one is the instruction selection. So here the nature of the, this is what we done it before, right? So we need to be choosing the instruction so that the instruction should be efficient and it should be speed, right? So when you consider the efficiency of the target machine, then the instruction speed and machine idioms are the important factors. The quality of code, generated code, can be determined by its speed and size, right? So here for this particular expression, they have written an assembly level language code, and here this part is a redundant one. Okay, so moving of the register value to a, and again here what we are doing for the next set of operation, that is d equal to a plus e. Again we are moving this a value back to the register, which this is not needed. So then this can be done like this. So we should Here we have three instructions. I mean, in total we have 6 instructions, so we are reducing that to 4 instructions. This is what we call it as an instruction selection and the efficiency, which will increase the speed of instruction execution also. Similar to it, as we discussed before, a for that a equal to a plus 1, instead of having these 3 instructions, we can write it in a single instruction of inc of a. And here is the register allocation. So here registers can be accessed faster than the memory. So whatever the variables that you have that need to be frequently accessed or be frequently used can be placed in the register instead of having that in the memory. So the instruction involving operands in the registers are shorter and faster than those involving the fetching is also will be faster. Okay. Following such problems arises when we use the register, right? So register allocation we need to take care of it, and register assignment also we need to take care of it. So when it comes for the register allocation, we select the set of variables that will reside in the register. What kind of register will be there, what kind of value will be there in the register, we will be decide when it comes for the register allocation. A register assignment means we will pick the register that contains the variable. So this is specifies which variable contains which register. Okay. Then certain machine requires even or pair registers, and we have some parity registers and all will be there. So that is what being discussed here. So here the division instruction, this is what is the division instruction d of x comma y. So here x is the dividend which will be stored in the even register and y is the divisor which will be stored in the normal register, and the even register is used to hold the remainder, and the odd registers will be holding the quotient value, right? And next one, the previous thing what we have discussed is that about the register allocation. Next one, the last issue is the evaluation order. The code generator decides the order in which the instruction to be evaluated is main thing. Then the order of computation affects the efficiency of the code also. Among many computational orders, some will require only few registers to hold the intermediate results. Okay, however, picking up the best order is the in general case is a difficult we call it as an NP complete problem, right? So we need to choose in the order which the instruction has to be executed. And now we'll talk about the runtime storage management. So the information that is needed during the execution of the procedure is kept in a block of storage called activation record, what we have discussed in the previous one in the issue, that is memory management. Whenever a procedure is called, a stack frame is allocated on the stack. See, for example, if we are using something called as an we are very familiar with this recursive function called fact of n. Okay? So that is calculating the factorial using recursive function, right? So we will be writing the base condition like n into fact of n minus 1. This is how we will be writing. So n into fact of here how we will be writing is that n into fact of n minus 1. So for example, if the value of the n is like 3, first time this fact function will be called. This will be inside the factorial function, that is fact of n. And whenever I call this function, and when it comes for this thing, here the function which will be calling itself, right? So how it will be called means 3 into, that is the f of 2, right? So this particular call will be placed inside the stack for execution, right? So the first one function will be called as fact of 3, right? So from this function call, what it will be done, again it will make a call like 3 into fact of 2, right? 3 into fact of 2 it will be called. Again from this it will be called as 3 into fact of 1. So fact of that is factorial of 1 is 1. So here what we will do is that we will return. So here after this 2 into fact of it will be called fact of 1. Again the fact of 1 will be called. So here it will be returning a number, right? So what it will do is that this after this it will be like 2 into fact of 1, right? It will be called as 2 into fact of 1. And here this fact of 1 will be called. So whenever the 1 is called, we would have written the code like if the value of n is equal to 1, return 1. So this particular thing will be removed and 1 will be returned. So here from where it is called? From this location. Okay, so here all the instructions will be popped in this order. At last it will come back to the location where it is called. This is what we call it as the, whenever a procedure is called, a stack frame is allocated on the stack like this. The information stored in the stack includes the return address, local variable, temporaries, return values also. Right? The two standard storage allocation strategies that we will have is that static allocation and stack allocation. So static allocation, the position of the activation record in the memory is fixed during the compile time itself. And when we will be going for the stack allocation is that if I want to create any new activation record, so I'll be pushing that in the stack, which means I doesn't know how much of memory it will be allocating. So a new activation record is pushed onto the stack for execution of the procedure. The record is popped when the activation is end. This is how it will be done here. So here the procedure's activation record has field to hold the parameters. Machine status information, the local data, temporaries, and other informations will be stored inside this activation record. Since runtime allocation and deallocation of activation record, which occurs as a part of the procedural calls and return sequence, we will be focusing on three statements, that is call, return, halt, and one more thing we call it as an action, which is a placeholder for other statements. And here this is what we have discussed is the static allocation and stack allocation. In the static allocation, a call statement needs to move the instruction to save the return address and go to transfers the control to the target code for the called procedure. So here if you take this the 3 address code, and this is the code for the function, that is C. So here we have an action, and again we have a call to P. So after this it will be coming to this call, and all these things will be executed, and again it moves back to this statement from where the function P is being called. After that it will be executing action 2 and then halt. So this is how your activation record will be for the function C and for the function P. So here activation record, inside that we will be having some array and then 8, and then it will be having some ij values will be there, and P function will be holding some buffer value along with that end. So after that execution comes here, and it will be executing all the rest of the statements in C. So move instruction, so which if you use move instruction, which will be saving the return address, then go to is nothing but which is used to transfer the control to the target code for the call procedures. And then next one we call it as an callee.static area and callee.code area. And here or these are the two constants referring to the address of the activation record and the first instruction for the called procedure. The entire activation record will be holding in callee.static, and callee.code area will be holding the address of the first instruction in that particular procedure. And here this is how the code will be executed, what we have discussed before. And here this is how the instruction will be written. Here this is the code for C, and this is action 1, and here it will be save the return address of 140 in location 364. 140 means it will be going to the next one, and all these things will be executed, and then here we have it returns to the saved address in the location 364. BR star means it is a branching like instruction, so here we will be holding the address, right, 140, so it will be going back here. So once it is done, it will be going back. See, from here we have a branch of 200, which means it will be going to the address 200 here. After executing, it need to be again move back from where it is called, right? So for that we will be storing the address, that is the 140 will be stored here. To after this, which statement need to be executed, that address will be stored in 364. So when I give BR star of 364 means it will take the value which is present inside the location 364. What is there? We have 140. So which will be so then it will be going to the location 140. From this the execution again it will start. Next one is the stack allocation. In static allocation can become a stack allocation by using relative addressing, right? So for storage and activation record, the position of the record for activation of procedure is not known until the runtime. So when it comes for static allocation, we know during the compile time, so we will fix the memory. But whereas when it comes for the stack allocation, so we don't know about the position of your record also. So in stack allocation, this position is usually stored in the register. So words in the activation records can be accessed as offsets from the value which is present inside the register. When a procedure call occurs, the calling procedure increments the stack pointer 1 and transfer the control to the called procedure. So after that, after executing all the statements inside the procedure, after that the control returns the caller, okay, and then it decrements the stack pointer and thereby deallocating the activation record of that called procedure. So here the activation record will be created once it returns to the caller from where this particular procedure is being called. So it will return to the caller, decrement the stack pointer and deallocate the activation record which has been allocated. So this is how your stack allocation will happen. So these are the certain instructions that we will be using in the stack. You can have a glance over this. And this is what is the static allocation, and I have given how the codes will be called and how it will be sent. Thanks for watching. We'll see you in the next video.